In this lab, we are going to configure a Route-Reflector. I have changed the topology within AS65001. Now we have more routers within the autonomous system, and I have also removed the whole BGP process from each router, as you can see. Now we are going to configure a Route-Reflector and Route-Reflector clients within the AS to solve the scalability issue of the full mesh configuration. In the previous labs, we have used the full mesh topology because we only had 3 routers. Having 5 routers with the full mesh, we would need 10 neighborship. So every router would need to form a neighbor relationship with every other router. That's for neighbor relationships for one router and 10 neighbor relationships total. Now, except one router, the Route-Reflector, every other router will have only one iBGP peer within the autonomous system, which is the Route-Reflector. So first, we select a router as the Route-Reflector. Let's say router 2 is the Route-Reflector, and the other routers are either Route-Reflector clients or just regular iBGP peers. Normally, all other routers should be Route-Reflector clients, but to demonstrate some important rules regarding the behavior of the Route-Reflector, we will have 2 Route-Reflector clients, router 8 and router 9. So they are Route-Reflector clients. And the 2 other routers, router 1 and router 3, will be regular iBGP neighbors of router 2. So as I have said, there is no BGP configuration on any router within the AS65001. The other routers are already configured, and they are advertising their own loopback address. So I haven't changed anything on those. So let's configure router 1 first, and only one router requires a special configuration within the cluster, and that is the Route-Reflector, router 2. Every other router within the AS is going to have one iBGP peer, and that will be router 2. So on router 1, we have one iBGP peer, and it will have one iBGP neighbor, the Route-Reflector, which is router 2, or neighbor 2222. We use the loopback address here, and the remote AS is the same. We will be using loopback addresses within the AS. So update source loopback 0. IGP is already set up, so router 2 has a route to 1111, which is the loopback 0 address, and we change the next hop address as we have seen in the previous lab, and that's done. Now I will configure router 3, router 8 and router 9, the same way, and I leave the Route-Reflector, router 2, to the end. And one important thing, it doesn't really matter if the router is a Route-Reflector client or just regular iBGP peer. The configuration on each router is the same. The addresses are different, of course, but the Route-Reflector client requires no special configuration on the client side. They will need the configuration on the server side, so on router 2. So let's move on to router 2. We have one iBGP neighbor. Let's begin with that one. So neighbor 10.0.20.7.7, and the remote AS is 65,007. And we have 4 iBGP neighbors. Let's configure those as well. First, router 1. And we configure the remaining 3 peers the same way. And now we should have 5 BGP peers. Let's confirm. I'll do show BGP IPv4 unicast summary. And now we configure router 8 and router 9 as Route-Reflector clients. It's a single command. So neighbor 8888 Route-Reflector clients, and for router 9 so now we have 2 Route-Reflector clients and 2 regular iBGP peers. To show run pipe section BGP, and we can confirm this by issuing do show IP BGP neighbors, but it is extremely detailed, as you can see. So let's jump to router 8. See, Route-Reflector client. And the same thing is true for router 9. Route-Reflector client. So we should have 2 Route-Reflectors if I issue show IPBGP neighbor pipe include Route-Reflector. Next, we take a look at 3 cases regarding the behavior of the Route-Reflector. So what happens if router 2 receives an NRRI from an iBGP peer, so from router 7, and it should forward it to Route-Reflector clients as well as non-Route-Reflector clients, so regular iBGP peers, and we can confirm this easily. 777, which is router 7's loopback address, should be reachable via router 2 on every iBGP router. On router 1, do show IP BGP. It is. Also on router 3 and on router 8 and router 9 as well. So it doesn't really matter if router 2 receives an NLRI from an iBGP peer, it forwards it to both Route-Reflector clients and non-Route-Reflector clients, and changes the next hop to its own loopback address, because we configured the neighbors with the next hop self statement. Now, what happens if Route-Reflector client, for example, router 9, sends an NLRI to the Route-Reflector? So the same rule applies here. The Route-Reflector should forward it to every iBGP and to every eBGP peers. But let's confirm. Router 9 is going to advertise its own loopback address or network 9999, and the mask is /32. On router 2, do show IP BGP, and we have it on router 2. Router 8, which is a Route-Reflector client, we also have the prefix here, but it isn't displayed here, but we have two additional path attributes. So if I issue show IPBGP with the prefix, here we have two additional path attributes, which are the originator and the cluster list. The originator is self-explanatory. It is the BGP router ID of the originator of the prefix in the local AS. And the cluster list, well, it's similar to AS path in a way that it is used for loop prevention. 2222 is the cluster ID of the Route-Reflector. So router 2, if we had multiple Route-Reflectors, we would discard the prefix if this list contained our own cluster ID. But because we only have one Route-Reflector and one cluster here, it is not an issue. But it is used to prevent loops within the autonomous system. And the prefix should also be present on non-Route-Reflector clients on router 1 and router 3. So let's confirm. And it is on router 1. And also on router 3. So now what happens if non-Route-Reflector client, router 1, for example, advertises a prefix to the Route-Reflector? So the Route-Reflector is going to forward it to every eBGP peer, of course, and every Route-Reflector client, but it is not going to forward it to other non-Route-Reflector clients. So the prefix won't be forwarded to router 3. So let's confirm this. In this case, we are going to use new loopback address, and we create a new prefix. So interface loopback1, because every other router within the autonomous system already knows the 1111 address, and it would simply cause RIP failure. So let's use this 11, 11, 11, 11 address with /32, and it is not advertised by OSPF, or at least I hope so, to show IP protocols. No, no network commands are defined here. So let's advertise this address with BGP. Network 11, 11, 11, 11 with /32 mask. And let's verify. The prefix should be present on router 2, the Route-Reflector, of course. And it is. And on the Route-Reflector clients as well, on router 8 and router 9. And that's right. But router 3 shouldn't have this prefix. So let's confirm. And it does not. But why? So the Route-Reflector does not forward the prefix because it was originated from non-Route-Reflector client, but router 3 should have received this prefix from his iBGP neighbors, router 4 and router 5. And that's right, both router 4 and router 5 forward this NLRI to router 3. But because the AS path contains AS 65001, because the prefix was originated here, router 3 simply discards this prefix. So let's confirm it. On router 3, we run some debugs, or debug iBGP. Let's run events, maybe, and updates. And let's force router 4 to resend the BGP updates. So clear iBGP outbound. See, here is the prefix BGP update received 11.11.11 network denied due to AS path contains our own AS. So this prefix was discarded because of loop prevention. But if we define router 3 as Route-Reflector client, it will learn this prefix. But first, let's turn these debugs off because it's very noisy. So undebug all, and on router 2, neighbor router 3, Route-Reflector client. And let's confirm. And indeed, router 3 now learn this prefix. And I would like to highlight one more thing. This is the packet capture of a BGP update message, which the Route-Reflector router 2 sent to router 9. The NLRI, so the prefix is 4444/32. So this was forwarded to router 2 by router 3. Here is the originator ID, router 3. The cluster list contains only router 2's cluster ID, which is the router ID by default. So we can confirm that router 2 is a Route-Reflector, and the next hop, which is router 3's loopback, is unchanged. So the Route-Reflector won't change these attributes for iBGP peers, although we have used the next hop self command. So router 4 forwards this prefix to router 3. Router 3 changes the next hop attribute because we have used the next hop self command for the iBGP neighbor. It forwards this NLRI to the Route-Reflector, and the Route-Reflector forwards it to every client or non-client, depending on the configuration. But the point is, it forwards the prefix with unchanged attributes, except it adds these, of course, for loop prevention purposes. But the next hop is unchanged. So every router should know this address to be able to install the prefix into the routing table. In this case, we do, of course, thanks to OSPF. But remember that the Route-Reflector won't change any attribute, and the receiving router should be able to reach the next hop address.